Hello, participants, and welcome to the last lecture of the phase 1 of the e-learning course in chromatography, jointly organized by Sheth M and Science College, Patan and DIPAM Foundation. Friends, the first 8 days in this e-learning course were really energetic and inclusive of a very well organized two-way communications. I received n number of questions from you, and I am still replying on one after the other. As promised to you, I'll complete all the doubts within the coming days, and for that, I'll be giving you instructions at the later stage of this talk. So, friends, let's begin with this today's lecture, that is numerical in chromatography, understanding the concepts of chromatography. Friends, apart from all the mechanism, instrumentation, applications that we have learned in these last 8 days, mathematical part is also that important when it comes to chromatography. Today, not much in detail, but we are going to study some 7 to 8 different numericals that will help us understand the mechanism behind a chromatography through a mathematical approach. So let's begin with this task by the first example. And before going into that, this is a very important small stanza that I am presenting before you, that the insights in chromatography can be achieved, that the better understanding of the concepts and phenomena involved in different chromatography techniques can be very well explained through calculating and understanding the terms that are involved in mathematical equations related to different techniques. As much as you understand the equations, the mathematical formulas, and their interpretation in each chromatography, you will be able to gain more and more understanding about that particular technique, the role of a stationary phase, the role of a mobile phase, the differentiation of a analyte from the mixture on the basis of its interactions, and so on. Many concepts that have still remained hidden from lecture 1 to lecture 8 might come up today. And if you still are having some queries, you can easily approach me. And today we are also going to generate a separate platform only for solving questions when we come to the end of this final talk of the online course in chromatography. First one, paper chromatography and the retardation factor values. Over here, study the interaction of the sample with the stationary phase, that is fundamentally a paper made up of cellulose, and elucidate its retardation factor value, helping to conclude the nature of a sample under the observation and comparing the analytes present in the sample. If you look over here, I have three samples, sample A, sample B, and sample C. And sample M stands for the mixture of all three. When these three samples were exposed to a mobile phase, keeping paper as a stationary phase, from the baseline, it was noted, this is the baseline, it was noted from the baseline that sample A is running the least, sample B is running the most, and sample C is somewhere in between the intermediate state of A and C. So from this itself, we can judge a little that sample A that is running the least has the highest interaction with the stationary phase. If cellulose is that stationary phase, then it is polar by nature, and therefore the sample A also must be polar natured. Whereas sample B that is running the most has the least interaction with the stationary phase and therefore must be the least polar or the highly nonpolar. And C, as you know, will be somewhere in between. So even by just noting the distance, you can identify its nature and its interaction with the stationary phase. But as we are interested in calculating the retardation factor values, if you look over here, that the total distance traveled by the sample A is 0.7 centimeter, whereas the total distance traveled by the mobile phase is somewhat 0.7 divided by 4.7. Sorry, the distance traveled by the mobile phase is somewhat 4.7 centimeter. So when we take the numerator 0.7 centimeter and 4.7 in denominator, we come with a value 0.15. Similarly, for sample B, it's 0.87, and similarly, point sample C, it is 0.38. if you just go with the theories that we have done during paper chromatography, the value ideally is between zero point 0.3 to zero point 0.7 or 0.25 to 0.75. So over here, 0.38 is one of the ideal most separation, whereas 0.87, that is corresponding to sample B, we can say that sample is moving very quickly with the mobile phase. So the nature of mobile phase and sample B must be same. Whereas the sample A is moving the least, so its nature will be very much equal to that of a stationary phase. And you can also reveal that as we know the stationary phase is cellulose and which is polar, A might be polar, B might be the least polar, and C might be the mid polar. Over here, looking towards the application, identification of each component from the mixture. Here you can see the component A, the component B and the component C having their separate runs. And when a mixture is running, you can correlate the three spots and you can very well identify, yes, that this spot is corresponding somewhere to B, this is corresponding somewhere to B, and this is corresponding somewhere to A. So friends, this is how you can find the corresponding points and identify each component. Even you can identify the impurity to an extent. So this is a very basic experiment and it's a mathematical representation for identifying the nature of a substance, for calculating its retardation factor value. Moving towards the second topic, and its mathematical representation, it's thin layer chromatography experiment. I have a question for you and I might request you at this stage that please keep a pencil, pen and a book with you because you will get a chance to calculate something where I might wait for 5 or 10 seconds. If in this experiment especially designed for you learners, if I say that mobile phase is hexane, stationary phase is silica gel, then what should I speak about the phenomena? Whether it is adsorption or whether it is partition. If we say that it is a completely dry silica gel, we should never get confused. It will be adsorption phenomena. Moving further a step, what about the order of retention? When will you be able to answer? When you will see that there are three components, component A, component B and component C. I will mix and give it to you and you must tell me that which of these three will be retained the most, which will be retained the least, and which will be in the middle. So let us skip this question a little late and move a step down. Nature of stationary phase. Nature of stationary phase over here can be detected in two ways. Number one, as our mobile phase is non-polar, stationary phase has to be polar. And second, silica gel is containing moisture, is containing the OH group, and therefore it is polar by nature. So over here, as of now, we have identified two answers. It's an adsorption phenomena and silica gel, that is the stationary phase, is polar in nature. Now, assume mobile phase to be ethyl acetate. Let us skip this portion for the later stage. And now we will solve the first part over here. If we have these three compounds and we try to solve the order of retention using silica gel polar as a stationary phase and hexane non-polar as a mobile phase. Among these three, the compound that is most polar will stay inside and the compound that is least polar will come out. Therefore, among these three, the first compound neither have any of the electronegative atoms like O, N, halogen, etc. So this is a complete non-polar molecule. And as it is a non-polar molecule and your stationary phase like silica gel is polar, you can see that this compound A will not interact with the silica gel or will interact least with the silica gel. So this will come out first. So the order of retention, if we are going from the quickest retention to the slowest retention, A will be quickly coming out and will be the least retarded. So you can write the answer in two ways. Let us write with the pencil in your book that compound A is least retarded, so will be eluted out first because the compound is non-polar and the stationary phase is polar. Now between B and C, OH and carbonyl both are present in C, whereas only carbonyl is present in B. So as OH is also present and carbonyl is also present, you have two electronegative groups. So this will be the highest polar molecule among the three. As this is the highest polar molecule and your stationary phase is also silica gel polar. So polar interaction will be highest and therefore the compound C will stay with the stationary phase for the maximum time. So the one that stays with the stationary phase for the maximum time is written as highly retarded substance. So C is the highly retarded substance. Now comparing B and C, B is less polar than C. As it is less polar than C, it will have less attraction with the silica gel compared to C. Therefore, it will be less retarded compared to C. So the highest retarded will be C, then will be B, and then will be A. So the order of retention from highest to lowest will be C greater than B greater than A. A will come out fast, B will come out afterwards, and C will come out the last. So C will have the highest retardation. Going inverse, elution will be highest for A. So if someone would have asked you what about the order of elution, A greater than B greater than C. इल्यूशन में जो सबसे पहले बाहर निकलता है वो सबसे पहले लिखा जाता है और रिटेंशन में जो सबसे ज्यादा अंदर रहता है उसको पहले लिखा जाता है. So C stays inside for the maximum time. So C greater than B greater than A. And in the elution, A greater than B greater than C. A is eluted out quickest, whereas C is eluted out the last. C stays in maximum, A stays in minimum. This was when hexane was used as a mobile phase. Assume the mobile phase to be ethyl acetate. What is the rate of retention? Speed of retention. Order will be same. Order will not change. But the speed will increase up to an extent. Why? Because now your mobile phase is also comparative polar than hexane. And you have two compounds that are polar. So compound B and compound C, which were coming out late, will now come out little early. And therefore, the peak will be observed a little early or the spots will be observed little early. So while changing the mobile phase, although we have told it to be a carrier, if you remember in every lecture I have told you that apart from carrier it has some effects. And these are the effects ethyl acetate is showing. So remember very well, ethyl acetate being polar will start dragging the B and C with it. So the time taken by B and C to come out from the end point of one side of the TLC to another side will now increase. So it will come out quickly and so time taken will be less. This is how ethyl acetate helps in decreasing the total retention time and increasing the rate of retention, means coming out quickly. Order based on the RF values will be same, order will be same, but the time will decrease. So the distance might increase, RF distance might increase, so RF value will increase. If it's 0.2, 0.3, 0.4, it might be 0.24, 0.34, 0.44. I hope you are getting the experimental mathematical part of thin layer chromatography. Justifying the nature of silica gel in chromatography. Silica gel is a polar stationary phase because of the presence of SiOH group on its surface, whereas modified silica gel surface can be converted into nonpolar propertide stationary phase like C18, C8, C4 and C2. The reason behind giving it over here is to prove that silica gel is polar by nature. I hope you have understand all the questions, all the blanks over here. If you have any query, you can contact me. Moving further, basic gas chromatography experiment. Let us assume that we have two compounds, cyclohexane and 1,4-dioxane. While comparing cyclohexane and 1,4-dioxane, over here and here, you do not have any oxygen atoms. But over here, you have two oxygen atoms. As you all know, oxygen atoms are polar by nature, electronegative by nature. It will make the molecule more polar compared to the next one. Now you read the question. Use the following gas chromatogram of a mixture of dioxane and cyclohexane eluted on a non-polar column. So your column is non-polar. When the column is non-polar, it's C18, C8, C4 and it's a reverse phase time. Over here, as the column is non-polar, it will attract the non-polar more and the polar less. So if A is coming out first, A is less non-polar. If B is coming out afterwards, B is more non-polar because it stays in for the longer time. So in the graph it will come out late. So of the two, as cyclohexane is more non-polar, cyclohexane has to be B and 1,4-dioxane has to be A. What is the identity of the substance labeled A? And explain how you deduce this. A is 1,4-dioxane because A is comparatively less non-polar and more polar, whereas our stationary phase is non-polar, therefore it will attract non-polar more and so it will come out late, whereas it will attract less to the less non-polar or polar, that is 1,4-dioxane, and it will come out early. Therefore 1,4-dioxane comes out first and it is represented by A, and cyclohexane comes out next and it is represented by B. This is how you get an idea when you have a basic chromatography based on the gas as a mobile phase. So this is how we can get an idea of separating two compounds. 1,4-dioxane is more polar than cyclohexane. The column is nonpolar, henceforth will retard the nonpolar natures for sample more compared to the polar nature and light. Cyclohexane, comparatively being more nonpolar, will be retarded than the less nonpolar or comparatively more polar 1,4-dioxane. The lone pair of electrons on the electronegative atom O is responsible for the decrement in the non-polarity of 1,4-dioxane. So these are few points which will help you prove 1,4-dioxane to be more polar than cyclohexane. Friends, remember these applications very well. We have done 3 applications up till now. The first one was the very basic paper chromatography. Second one was the thin layer chromatography where the stationary phase was silica gel. And today we have justified very well silica gel as a polar surface. If I am not mistaken, someone has asked me about silica gel's nature, and today I hope if he or she is on the lectures, they will understand it. And the third one was gas chromatography experiment. Moving further, let us identify the order of elution. In gas chromatography with a polar column, if your column is polar, butanol, methanol and water. Among these three, butanol, methanol and water, which one will stay in for the most time and which one will go out easily? Friends, water, methanol and butanol. Water is the most polar, then comes methanol and then comes butanol. As you see over here, if these are your samples, these are my samples, assume, then water will stay in for the maximum time. This is just for an understanding. Water will stay in for the maximum time, whereas butanol will come out early because the column is polar. Getting exact inverse of it, if the column is non-polar, butanol will stay in for the maximum time and water will come out first. This is what you should know. I have not written the orders over here. These are just questions, just for the sake of learning. As the column is polar, water will come out last. It will be retarded the most. Whereas over here, as the column is non-polar, water will come out first and butanol is retarded the most. So this is how small things that we have learned in this all days chromatography will help us to elucidate even the nature of the chemical compounds. Basic HPLC experiment. You are given a sample composed of 3 components A to C, means A, B and C, with different polarities. The sample A is loaded, or sample A, B and C are loaded on a C18 column and eluted with 30% methanol water. Now see, when you write 30% methanol water, it's a polar combination. So if your mobile phase is a polar combination, your stationary phase C18 being a non-polar combination, it is very clear that it's a reverse phase chromatography. After eluting with 10 ml of solvent and collecting 1 ml fraction, compound A and B are found to be in the third and sixth fraction. Third means collected from first, second, third bottle. So fraction A or compound A is coming out first. Compound B is coming out next. Because third comes first, sixth comes afterwards. If A is coming out first, your stationary phase is non-polar. It means A has least interaction with non-polar. So A will be the least non-polar or polar. whereas the B comes out afterwards. So you can identify it from this much only. So compare the polarity of A and B. As A is coming out early, stationary phase is non-polar. Between A and B, the one that comes out early has less interaction with the stationary phase, and therefore A over here is more polar than B because it is coming out early. It has no interaction with the stationary phase. So between A and B, A is more polar compared to B. Moving a step ahead, after eluting with excess of 10 ml, compound C has not yet eluted. आपने एक बार 10 ml सॉल्वेंट डाल दिया, दूसरी बार आप 10 ml डाल रहे हो. Even then, after adding twice, 10 ml was added initially, 10 ml was added excess. Then also C did not come out. Means C is still sticking with the stationary phase, so long retention time. When such is the case, you should not keep on adding new and new mobile phase, but you should change the polarity of mobile phase. As you know, C is staying inside. Your column is C18, means C is also C18 type nature, that is non-polar. Now, if I want to bring the non-polar out and the mobile phase used earlier was not able to do so, that is 30% methanol water, where water is more, methanol is less, so it is highly polar. If I increase the content of methanol and decrease the content of water, the polarity will reduce and go towards non-polarity. We cannot exactly say non-polarity, but the polarity will reduce. And it is like tau and delta. So if polarity will reduce, it is going towards non-polarity. And when its polarity will go down, it will now have the capacity to drag that sample C out. So if C is not coming out and you want to bring it out, you have to change the composition of mobile phase. So this is where mobile phase game came into existence. I will explain it over here. Sample C is the highly nonpolar sample with maximum retardation time due to highest interaction with the stationary phase. Among A and B, A is eluted in third fraction, that is first, will have the least interaction with the stationary phase and least nonpolar nature. Because stationary phase is nonpolar, it is coming out quickly, so it is not nonpolar. It might be polar. Followed by the sample B eluting second with more nonpolar nature compared to sample A. Over here, I will read it again, and if we could find some justification, we would add. Among A and B as a sample, A is eluted third, will have the least interaction with the stationary phase and the least non-polar nature. आपका stationary phase, your stationary phase is non-polar, C18. If sample A is coming out quickly, it is not non-polar, it is polar. But B comes after A. So B is sticking a little with the stationary phase. So it has little nature of stationary phase, and that little nature is more non-polar than A. So among A and B, B is more non-polar, A is less non-polar. और उल्टा भी बोल सकते हैं. You can spell it reverse. If A is least non-polar, it is more polar. If B is little non-polar, it is less polar. So you can go both the ways. Don't get confused. Listen it very carefully. You have the option of rewinding and listening. Don't panic. This is what chromatography teaches us. Again for the last time. Among A and B, as the sample A comes out first, stationary phase is C18 non-polar reverse phase. It will catch non-polar but will not catch polar or less non-polar. So A is coming out quickly, so it is less non-polar or more polar. B is coming out next, so B is comparatively more non-polar than A. Sample C does not elute swiftly, even after extra elution, indicates to be highly nonpolar and require comparatively a less polar mobile phase for its elution. When you are not able to remove a sample from the stationary phase interaction, you need to make your mobile phase powerful to catch it. And if you want to make mobile phase powerful to catch a non-polar sample, the polarity of mobile phase has to be decreased. So if 30 is methanol and 70 is water, it is more polar. But if 70, 80, 90 will be methanol and 10 will be water, then its polarity will decrease. And if polarity is decreasing, non-polarity is increasing. And therefore now it will catch the sample C and bring it out. So friends, this is how we can justify component A, B and C in a basic HPLC experiment over here. Moving further, effect of mobile phase on a chromatogram. Here you can see two chromatograms, chromatogram A and chromatogram B. Chromatogram A, peaks are very near to each other. There are 8 compounds. We are not interested in compounds as of now, but there are 8 compounds. In chromatogram A, you see, you cannot separate even 8. But in chromatogram B, beautiful. You are able to identify few of them separately. Although 2 and 3 are not getting separated completely, even 6 and 7 are not completely separable, but still, it is better than A. When you compare A and B, you like B comparative to A. What is the reason? Stationary phase are same, flow rate is same, compounds are same, instrument is same. Then mobile phase plays an important role. If while performing an experiment having 8 component mixture, if I get a graph like this, I should not panic and ultimately change a column. Stationary phase jaldi se nahi badalna chahiye. Why? That column is somewhat around 30-40,000 and it takes at least 45 minutes to 2 hours to change it. And industry is never interested in investing 2 hours. So there should be some chemistry, some science where you can broaden the difference or the gap between them. I'm not asking you to broaden the peak. I'm asking you to make the distance between the two peaks visible. And to do that, mobile phase plays an important game. Chromatogram B was recorded on the same column and with the same sample as chromatogram A, but the separation is different. Justify this. Why? Because of the effect of mobile phase. Now let's see what was that effect. Justification. This is because the mobile phase was changed between the two separations. Chromatogram B was recorded using a mobile phase with a lower eluent strength than chromatogram A. Friends, mind it, possibly I have written by mistake B. I'll read it once so I can get an idea. This is because the mobile phase was changed between the two separations. Chromatogram B was recorded using a mobile phase with a lower eluent strength than chromatogram A. Over here, pardon me, A will come. What is written over here? It is if while performing the experiment in A, the mobile phase that was used was very much powerful and it was dragging all the compounds with itself and not allowing stationary phase to catch or retard the sample. It means all these compounds were having the same nature as the mobile phase. And you can guess it easily being a science background person if you look towards the name, leaving one or two. Alcohol, phenol, acetophenone, benzoin, benzoate, dimethoxybiphenyl. 1, 2, 3, 4, 5 and 8 all having somewhat polar groups. Toluene might not have, 2,6-dimethoxytoluene might not have, but others have. Depending on this, if you check, you can say most of the compounds are little bit polar. So if the compounds are little bit polar, you should have a non-polar stationary phase, but the mobile phase should be somewhat mid-polar. But if by mistake you take a highly polar mobile phase, it will attract all the samples together and drag them away. And when all the samples will come out quickly, the graph will start from the very initial part and you will get all the peaks together. You will not get a separate peak and also the peaks will come out early. So to overcome such an issue, what has to be done? Chromatogram B was recorded using a mobile phase with a lower eluent strength than chromatogram A. Chromatogram A, mind well. So what did they do? They now changed the composition of mobile phase and made it little lower eluent strength. Means the nature was little bit made away from the nature of samples. So it could drag but slowly. For example, Chromatogram A may have been recorded at 90% methanol and 10% water, whereas chromatogram B may have been recorded at 50% methanol and 50% water. These are just an idea. Second important thing I want to draw your attention, keep focus on this photograph more on the distance between the peaks. Do not worry more or do not think more about the name, their structure and their position over here. We are as of now not interested that which should be positioned where. We are interested that if we are getting such type of graph which is not good, and we want to make such type of graph which is good, which is authentic, which is responsible, then we should make changes in the mobile phase. So we are as far learning the key effects or impacts of mobile phase. Water, acetonitrile, methanol are the possible mobile phase. UV visible detectors are used over here because all these compounds that are shown on the screen are organic. All non-polar stationary phase is allowed because most of the compounds are polar. So friends, this is a justification on the effect of mobile phase on a chromatogram. Hope you are understanding, but please keep two things in your mind very clear. Number one, over here it's A, and number two, these values are just to make you understand, but the main theme behind it is that if you want to make a good clarity in your graph and if you want to remove this overlap of the peaks and make it crystal clear like this, you should change the mobile phase and not directly move for altering the stationary phase columns. Understanding the term unretained peak, improper and proper separation. There are few compounds which, when injected in a column, are not at all attracted towards stationary phase due to some nature, and they come out quickly together with the mobile phase. Together with the mobile phase. I will explain it. You go back in one of my example of that boat and river. Always river is moving ahead and boat is being dragged with the water. But I told you on that day, boat cannot move ahead of river, but boat can move along with the river's front zone, front line. So the same thing happens over here. The sample which is not at all attracted with the stationary phase will move constantly with the initial layers of the mobile phase and will come out the earliest without any interaction with the stationary phase. These are the most improper things, and they are coined as unretained peaks. Unretained peaks. Not at all retained, not at all retarded. Apart from these, when the peak appears to be like this, compound X and compound Y, the peaks are not at all good. No sharpness, nothing. These types of peaks are called improper separated compounds. The compounds are not properly separated. And when you get such type of peaks, you can generally call them proper separation. Over here, comparatively proper separation is there, but improper separation is coined because of the impurities present in the stationary phase. Sometimes even there are air present in the stationary phase which could lead to such kind of humps. So this is just for an understanding. We wanted to add something which was apart from calculations. This is one particular slide that I am adding. HETP. If you remember on that day, height equivalent to theoretical plates, I made you draw some columns in your book. They must look like this. One column with bigger size stationary phase, second column with smaller size stationary phase. Now you can easily see that over here the number of layers will be more. As the number of layers are more, the size of particle is small, it will have more surface area. Whereas over here, number of layers are less, particle size is big, surface area will be less. Therefore, when you are comparing these two, over here the separation will be poor, over here the separation will be more good than this. Because as the stationary phase size decreases, more and more surface area, more and more interaction, more and more layer to cross, and therefore more good separation. So this imaginary surfaces, these imaginary layers are called theoretical plates. So remember, very simple. More the number of theoretical plates, more excellent is the separation. Less the number of theoretical plates, less excellent is the separation. And do not panic when I say that when I shift from a bigger molecule to a smaller molecule, the surface area increases, it actually increases. How I'll explain you. If I have a cube, it will have 6 surfaces. But when I'll cut it down, the surface in total will increase. How I will tell you. You imagine a cube, it is all side equal. When I'll cut it, the number of surfaces were earlier very good, 6. Now if you will start measuring the surface again, you will have one extra surface that is cut. Because when you are cutting into two halves, one part was there, one part has increased. So always remember, when you come down the size, generally the surface area increases. And over here, if the surface area increases, the interaction increases. And if the interaction increases, the separation increases. And if the separation is good, everything is good. So, more the imaginary theoretical plates, more better is the separation. So this was those columns. I think few of you might have got it correct. The equation to calculate the theoretical terms, imaginary terms, I call it terms, plates, is number of theoretical plates is attributed to the length of the column used in the experiment and the size of the stationary phase microgranules filled in the column. So from this end to this end is capital L, the length of the column. And this very little distance is the height of each layer. So N represents the number of theoretical plates, L is the total length of the column, and H is the height of each plate. So when I use the formula N is equal to L by H, I end up with number of theoretical plates. And now I'm speaking it again. Length is constant in both. Length is constant. So if I decrease the height of each layer by making very fine stationary phase particles, I will increase number of N. And if number of N is more, separation is best. How to decrease the layer size? Just by taking small and small micron particles. If you are using 5 micron, start using 2.5. If you are using 2.5, go to 1 micron. The lesser the micron size, the lesser will be the height of the layer. The lesser will be the height of the layer, more would be the surface area, and more would be the surface area, more would be the theoretical plates, and more would be the theoretical plates, more will be the separation. Length of both the columns to be same material of stationary phase and mobile phase, analyzing the same sample, only the size of stationary phase is varied. What will be the conclusion? Conclusion I have already taught to you that between the two columns, the column having the smallest stationary phase will have the best results. Let us go once again step by step, especially for my students of the BSc and the MSc program. HETP, solving the query. As the length of the two column, stationary phase, mobile phase material are similar, the main focus of us is only on the size of stationary phase. When the imaginary height of the stationary phase is less, how can you make it less? As the size is less, it is very small microns. Number of imaginary plates will be more owing to the equation N is equal to L by H. When the imaginary height of the stationary phase is more, as the size of the stationary phase is large microns, number of imaginary plate will be less. Less plate, less separation efficiency. More plate, more separation efficiency. So good number of N, good is the separation efficiency. Less number of N, less is the separation efficiency. So this directly affects the property of separation and quality associated with it and can be directly observed on a chromatogram. If separation is very good, the two peaks will be completely appearing separate. I am moving my hand again. Peak number 1, peak number 2. But if the two are not very well separated, it will be like this. One peak is not yet over and the second one will come. And I'll explain you, so do not worry. But my focus today in this talk was specially to make you aware that how small mathematical formulas can give you an idea regarding what will be your answer of your experiment. Over here, I just want to make you aware of the nature. See, among these four, this peak is the best. Why? Because one peak is coming completely down and then the second peak is going up and coming down. So this is called the best efficiency of the column. When this peak has come, the stationary phase of the column, the mobile phase of the column, the size of the particle, everything would have been the best. Everything would have been the best. Then and then only you will get such a good thing. But away from this very good peaks, imagine these peaks. One compound is coming out. Before it comes out completely, second compound is coming out. एक कंपाउंड कब पूरा बाहर आए ऐसा माना जाएगा? When will you think that one compound has completely come out? When the peak that is going up completely comes down back. In this four imagine, in this images, in this image you cannot see the peak going up coming down completely. It indicates that the first compound before comes out completely, second has started coming out. Means there is not any much distance identified between two compounds. Now imagine when the two compounds will have less distance between them, when they are not properly separated, when there will be no properly separated, when they have less hindrance. When will they have less hindrance? When the layers will be bigger, because when the layers will be bigger, there will be less number of layers, and when there will be less number of layers, you cannot separate the component properly. Remember the marathon race? More the hurdles, one will run back, one will run away. You can separate, but you will only keep three hurdles. A fat fellow and a thin fellow, both will cross. You won't be able to identify the winner. Similarly, before the first compound comes out completely, second has started coming. So not a good sign, and this type of things happen when you are using this type of big micron size of stationary phase. But if I use small size of microns, beautiful size of microns, needed or required size of microns, I get very good peak. Then you will ask me a question, sir, then what about this and what about this? I will give the answers. I will give the answers. In both these, the microns are very less, very tiny. After coming out of one compound, if the second compound comes after a long time, then also it is not good. After first compound, in a very little time the second should come out, then also they are separated. But after one compound is coming out, you have to wait for 1 minute and then the second compound comes out. It is not a good sign. So these two pictures are related to very small size of micron, even small than required, very much separation. This is very big size of micron, very poor separation. And this is the best size of micron required for this particular experiment. So the best separation. You can see over here, poor resolution, poor efficiency, good efficiency, satisfactory analysis time, good resolution and selectivity, but too long analysis time, poor efficiency. Efficiency is not good. Excessive resolution, excellent selectivity and efficiency, analysis time too long. So in this and this, analysis times are too long. We do not want too long analysis time, too short analysis time. We want a perfect analysis time. So from here you will learn that HETP, height equivalent to theoretical plates, is one of the governing factor for the separation efficiency. If you want a good separation, one peak going up, coming down, after 2, 3, 5 seconds, second peak coming up, going down, then the micron size selected for the stationary phase should be very good, very excellent. This is, friends, the application of HETP mathematical formula in the separation technology. Estimating the number of plates by half peak height method. Friends, over here the formula is N is equal to L by H. But sometimes we have L, we do not have N, we do not have H, and we are asked to find out H. I'm repeating it again. When you have both L and H, it is fine, you will get N. Sometimes you only know the length of the column. You don't know even the particle size. You don't know even the N. And then you are supposed to first find N and then give the answer of H. So N will come in the denominator and H will come in the subject. So H is equal to L by N. See what happens. W is the peak width or bandwidth. So from this particular point to this particular point, this band or this gap is the width. The half of WB is W1 by 2. Smaller plate height, translates into symmetrical, narrow, Gaussian-shaped chromatical peaks. Reverse is true for the peak with greater peak width. If the width is more, then reverse is the true for the peak with greater peak width and smaller peak width. If you see this dotted line going up, coming down, if the peak was not this much broad but a little sharp, then this would have been correct. Smaller plate height. Why? जितना plate height छोटा होगा, the more the less the h. It comes in the denominator L by h. So denominator is small, n will be large, and if n will be large, separation will be beautiful and sharp. But here the problem is we don't know h. So we have to first find n and then go for h. So for finding out n, we have two formulas. 16 into bracket tr by w square, 5.54 into bracket tr by w square. Over here w is this width, tr is the retention time taken by a sample from one end of the column to another end of the column, and 16 and 5.54 are the values of the coefficients that are calculated from the column performance used in the experiments, and generally they are given in the pharmacopoeia, because without pharmacopoeia pharmaceuticals are nothing, and in pharmacopoeia these values, their significance are given and they are called coefficient values. So over here, if you know the width, and width can be known from the computer. If I'll ask computer to give me this distance, it will give. I'll put it over here. This will be the time provided to me by the computer, TR retention time. 16 is the value, I'll get my answer n. And in the formula, now h is equal to L by n. L is the length of the column I know, n I have got. So now I will get the height, and lesser the height, more better the peak, more better the separation. So this is how, if you don't know n, if you don't know h, you can first find n and then go for h. Solve the following. The column length is 25.7 units and the flow rate is 0.313 ml per minute. A chromatogram of mixture A and B resulted in the following data. Calculate number of plate and height of each plate. Number of plate is n and height of each plate is h. So you don't have n, you don't have h, you only have the length of the column. A has a retention time of 6.8, B has the retention time of 14.5, width of the peak base A is 0.56 and B is 1.18. So friends, over here, this is W and that is TR. So when I will use them in the formula, I will get an approximate answer 2360 number of plates for A and 2420 number of plates in context to B. So nearly the number of plates are same. You are always supposed to take the average because all these experiments are carried in a single column. And the height of each plate will be somewhat around 0.01 units. I am using the word unit over here. It is centimeter. Don't worry. I have calculated them. You can also calculate using the formula. What is the formula that you will apply? This 16 into bracket tr by w whole square. You will get n, that is this. Now L divided by n. L is 25.7. So you will end up with these values. Average values are always taken of all the samples. This plus this divided by 2. 2390 is the number of theoretical plate approximate. And height is equal to somewhat 0.01 average. So friends, this is how we are getting n. We had L, so now we can get the values of h. So this is the HETP, N, L, H, its application and their results. Remember, more the value of n, very good is the separation. Less the value of h, very good is the separation. Because less the value of h, more will be the quantity of n, and separation will be very good. I am okay with it. You should also be okay with it, and we are moving further. Calculations related to resolution. Given the chromatographic below, actually one chromatogram with two parts expanded. Over here if you see, there are 6 different peaks. Calculate the resolution of the first 2 compounds. Means I'll go for these 2. And is the analysis time unnecessarily long? If yes, why? Yes, it is long. Why? Because it started from here. Somewhere over here it is 10 minutes. It is 15 minutes over here and it is 25 minutes over here. I told you, sometimes there is a very much big difference between 2 peaks and it is useless. So yes, analysis is unnecessarily long after the 5th compound comes out. The time between the fifth and sixth is too long and it is not good. So there is a gradient mobile phase procedure in every chromatography. After the fifth compound comes out, the scientist will adjust the mobile phase gradient composition in such a way that the sixth compound will come out early. So yes is the answer for the second one. Why? Because the distance between the fifth and sixth on the graph is more, which indicates that the retention time is more. Sixth compound बहुत ज़्यादा stationary phase के साथ रहा है. Sixth compound is staying for a too much long time with the stationary phase. So you have to use a new mobile phase. Changing during the process, it can be done. And this mobile phase will now drag the sixth compound early and retention time will decrease. Application we learned earlier in the same lecture. Calculate the resolution between the first two compounds. This is the formula for resolution. Resolution is equal to 2 delta Z divided by WA plus WB. Now, delta Z is nothing but the retention time of second analyte minus retention time of first analyte. If you see over here, we are discussing these two red compounds. Over here, the retention time is exactly this value, which is somewhat around 12.4 for compound A, and this value, which is somewhat around 13.45 for B. So retention time of B minus retention time of A, that is 13.45 minus 12.4 whole divided by this width and this width. If this width is calculated from here, it is 12.2, somewhat around 12.65. So what I did, I made it a round figure, 12.1, 12.2, so it is 12.15. 12.65, so 0.5 is that value, the width, and over here it is 13.2 to 13.7, so again 0.5. So when I'll solve this, I will get my resolution value around 2.30. Friends, ideally, people after a lot number of experiments have come out with a conclusion that resolution value should be somewhere around between 1.5 to 2. Then what if you get more than 2? What if you get less than 1.5? I am getting more than 2. It means the peak are very much away from each other. They can be less. If they come together, means after one peak, second peak should start. If that is taking a longer time, resolution will be more. But sometimes, as we saw earlier, एक peak पूरा आता नहीं है, दूसरा शुरू हो जाता है. Peak 1 is not completely vanishing and peak 2 is coming. It's a bad resolution. So its value will be less than 1.5. Over here, as the first peak comes down somewhat around 12.8, the second peak should have been started around 12.9 to 13 over here. It means like this and suddenly like this. But as it is a little late, resolution is more. But I have kept a picture of a standard resolution. If you see over here between A and B, the peak A is coming down and peak B has started. See the resolution. It is 1.5. Over here it is 2.3. So ideally, people say that between 1.5 to 1.8, 1.9 it is very good. But 2.30 is little bad as the difference is more. I can explain it over here. Have a look. See, over here resolution is bad because first peak is not coming out completely and second is coming. Over here the resolution is even bad because the difference is more. Over here also difference is more, but over here it must be somewhat around 1.5, 1.6, 1.7. Here very less than 1. Over here much greater than 2.3, 2.4. So even this is not too good, even this is not too good, but this is one of the best. So resolution helps us in determining how would be our peaks. Sometimes what happens? A senior who is working in pharma company or your PhD guide or your mentor or your senior working in your lab, he will be sitting outside and enjoying the tea. I am taking it in a very lighter words. A junior will be working in the lab. He will suddenly come out and say, "Sir, I am not getting proper graphs." Sir will not come inside. Senior will not come inside. But his experience on the RS value will come inside mentally. He will just ask you, go on the computer and tell me the RS value. That is resolution value. You will say, "Sir, 2.6. He will say, "No worries, you change so and so in the mobile phase and meet me when the value comes around 1.9 or 2. Means he has got an idea that as the resolution is larger, The second peak is coming out late. So he will make you change the mobile phase in such a way that the second peak will come out early. You're getting my words. So just by knowing the mathematical answer of RS resolution, a person can solve or can bring the retention time down. This is the magic of mathematics in chromatography. I hope you are getting what I am speaking. So these are, friends, some of the topics that is a little mathematics that can help us grow in chromatography, helping the researchers. Each formula associated with each chromatography technique has its own importance. Quality of the stationary phase can be determined. Interaction of the sample with the stationary phase as well as the mobile phase can be determined. Flow of the mobile phase and its effect on the separation of analytes can be determined. And sometimes interaction between the two analytes can also be determined. So these all are the fundamental points that can be known just by knowing the answers that come out from the mathematical equations in chromatography. There are few researchers today also. They do not look at even at the graph. Just by knowing the RS value, just by knowing the retention time value, they will give you the suggestions whether your experiment is totally correct or has few errors and alternations are needed or not. This is maths in chromatography. Concluding remarks. Friends, the presentation here is concerted to only one-fifth of the formulas utilized in the field of chromatography. Several untouched equations still are left to be applied, understand and discuss. So friends, this was a little bit of mathematics in chromatography. You can have much more. You can go through it. Even I will come back after a month or two with the upgraded version of the online course in chromatography where I'll be discussing all these points thoroughly, because now it's a beginner's course which has come to an end, because today is the ninth day of our journey. Although I have not met you all, but I am connected mentally with you all. And it is really feeling bad for me that from tomorrow onwards, we will not be in touch regularly. But I promise I'll be back very soon with you all with something new, something helpful to both of us in our life. Friends, thank you once again. It was really a nice experience and a fruitful journey for me, learning from you people, your questions, your suggestions, and your queries. I am very much open. Feel free to bang me with the questions because your questions will help me to learn and I'll get back to you. It's a promise. Friends, I have received many questions from you, but I was unable to answer all because I was here managing all your tasks of your online course. But tomorrow, when your exams will be there, along with your test, I'll be sending you few other links, of which one link will be regarding your queries. In that link, I will ask for your name, few other information about you, and I leave empty space where you can write all your doubts with proper references. Lecture 1, day 2, day 4, day 7, and I promise that I will answer each one of them in a chronological order. So you will just fill that form completely and give back to me. There will be few other announcements that will be coming tomorrow for you people along with the test. So when tomorrow, that is day 10 of our course, you appear for the test, before filling the form, read the instructions carefully. The name that you will write over there in your main exam, the certificate will be issued in the same name. No changes will be altered or accepted once that form is submitted. So please write your name very correctly. No one will be there responsible to change those names. Second important thing, you will have a 50 questions, 100-mark paper, and you should at least correct 20 questions out of those 50 to qualify your course. 20 correct answers, 40 marks is the minimum criteria for you to qualify the test. Once you submit the test, you will get your marks on the screen, but you will be issued certificate in the next 10 days in the form of soft copies. If you are not getting disturbed, Friends, do not leave the Telegram group that we are in, because all the updates I will be sending for the whole of my life on that special group, unless and until some technical default comes. So if you have really enjoyed, be in touch. I'll be very soon coming back to you after the successful completion of phase 2. This is phase 1. But those who have missed phase 1, the same copy of phase 1 is in there in phase 2. I'll be coming back for phase 2 also. And once I complete phase 2, after that, phase 3 will be something new, where both the candidates of phase 1 and phase 2 will be eligible, as they are now a successful beginners in chromatography. Once again, thank you all for your patience listening, for bearing me these 9 days. I have really learned, enjoyed a lot from you, and hope your 9 days have been fruitful and not a waste. Now, the last announcement before I shut it off. There will be some advertisement going on in your group of phase 1 regarding phase 2 also. But as you have already participated in phase 1, you are not required to participate in phase 2, which is going to start from 7th of May itself, because that is the same copy of phase 1 for those who have missed phase 1. But friends, there will be a something more added in phase 2, which is not scientific part which is to be added, but that is a language barrier that we are going to add. I have received many suggestions that few of my BSc students from the state of Gujarat are facing a little difficulty. So I will be specially adding for you people a separate lecture on these 9 topics for the round 2 in the Gujarati language. A last announcement before we leave in a little Gujarati, and again I'll come back to our own English language. જે મિત્રો આ પહેલા રાઉન્ડમાં હતા અને આખું રાઉન્ડ અંગ્રેજીમાં ભણ્યા છે, અંગ્રેજીમાં પરીક્ષા આપી છે, તેઓ માત્ર બીજા રાઉન્ડમાં ફરીથી જોડાવું હોય તો જોડાઈ શકે છે. એટલા માટે કેમ કે બીજા રાઉન્ડમાં બધા લેક્ચર તમને ગુજરાતીમાં મળવાના છે, પરંતુ બીજા રાઉન્ડમાં નવું કાંઈ નથી મળવાનું. એટલે કદાચ કોઈને એવું હોય કે ના મારે જોડાવું નથી તો ચાલશે, કેમ કે એમાં કશું નવું નથી. પણ કોણ જોડાઈ શકે છે? જે લોકોએ પહેલો રાઉન્ડ કર્યો જ નથી છતાંય કોઈને જોડાવું હોય તો મોસ્ટ વેલકમ. ખાલી એટલા માટે કે તમને ગુજરાતીમાં ભણવાનો લાભો મળે. So friends, all other instructions regarding the tomorrow's test, the certificates, upcoming updates, I'll give you through our Telegram subscription page. Be in touch, be healthy, and live healthy in this COVID-19. Thank you once again.